Alright, hello everyone. This is Orion's brightest star, and today we're going to be going over a little bit about curvature, and then we're going to cover two important theorems in differential geometry. So let's start off with curvature. So what I'm going to do today is pretty simple. I'm just going to go over a couple useful formulas for curvature. So if we have a general curve, the curvature is the derivative of the unit tangent, the norm of that, over the norm of the velocity, which is the norm of the perpendicular component of the acceleration over the square of the norm of the velocity. And if the curve is unit speed, it's the norm of the acceleration. So this is for just a plane curve. So we're working in R2. So the sectional curvature is the derivative of our angle function. And we can represent the sine curvature as this formula. If we express a curve in terms of functions x of t and y of t, then we have this formula as well. So this is if gamma of t can be expressed in the form of t f of t. So we have that formula. Now for a space curve, so now we're in R3, the curvature is simply velocity times acceleration, and the norm of that over the norm of velocity cubed. So that's basically all we're doing for curvature today, but there are two theorems that we're going to look at as well today, and we're going to be going over the proofs for them, and it's pretty long, so I guess let's begin. So suppose that we have a plane curve, and it's simple and closed. And suppose C is the trace of gamma. There are two theorems that we can talk about here. Hopf's Umlaufsatz. Let me spell that out. And that basically just says the rotation index of gamma must be positive or negative 1. So if we have a simple closed curve, the rotation index must be positive or negative 1. we also have the Jordan curve theorem. And that basically says that the plane minus the curve, the set of points in the plane, minus that are not on the curve, has two path-connected components. Their common boundary is C. One is bounded, the other is unbounded. So before we begin, let me talk a little bit about what the term path-connected means. It's a term in topology, and what it essentially means is we have a space. This is path-connected if for any 2 points A and B, we can draw a path gamma which is a mapping from an interval to the space itself from A to B. So it's path connected if we can draw a path between any 2 points in the space. So let's talk about orientation of curves. So a simple closed plane curve is positively oriented if the rotation index is 1 or equivalently, the interior of the curve is on the left as one traverses gamma. So if you can imagine this is our interior of the curve, if you imagine traveling through the curve, you can see that to the left is the interior. And also we have rotation index 1. Otherwise, the curve gamma would be negatively oriented. So this is positively oriented, and a curve like going clockwise as you can see, the interior is to the right as we traverse the curve. Furthermore, we're going to create a proposition, but we're not going to prove it right now. If we have a function f from an interval a, b to the circle, so something like that, then there exists a continuous, oh, this is continuous as well. Angle function, theta, which goes from A, B to R, such that we have f of t equals cosine of theta of t, sine of theta of t. and we have that the degree of the function f, degree of f, is 1 over 2 pi of theta of b minus theta of a. One last thing before we prove the first theorem is a lemma that we will need. That's in the book. We don't need that numbering. Suppose we have two functions such that we have this, and f2a equals f2b. If f1 and f2 have different degrees, then there exists some t naught in between a and b, including a and b, such that we have that. So this lemma, for the interest of time, I'm just going to skip the proof. It's pretty simple though. Now we have everything we need to prove the first theorem. Okay, so remember we have a curve that is simple and closed, and C is the trace of gamma. Suppose that we have a point on the curve such that the trace is on one side of the tangent line to C at P. So what that basically means is, suppose we have like it goes this way. This is gamma of A equals gamma of B. Suppose we have a point P here, and its tangent line seems to be such that the trace of the curve is on one side of the tangent line, not the other side. There is a more rigorous way to justify this, but since this is just going to be like a quick overview, I'm just going to breeze right through. So now let's parameterize it, or parameterize by arc length, such that gamma of A equals P. So this is no longer the case. Gamma of A. So let's talk about the triangle T, which is the set of T1, T2, such that A is less than or equal to T1 is less than or equal to T2, which is less than or equal to B. And you're probably asking me, well, how is that a triangle? Let me show you. If this is our T1 axis and this is our T2 axis, then that shape would be T with everything inside. now let's define this function such that we have okay, so basically what we have here is we have a function that takes 2 points on the curve. Let's say we have a point 1 and a point 2. And oh, and it gives us the unit vector from the first point in the direction of the second point. So that's basically what it means. If the 2 points are the same, then it's basically just the slope of, it's just the unit tangent. And if one of them is gamma of A and one of them is gamma of B, and that is pretty important, then it would be you could imagine a vector pointing from gamma of A to gamma of B, which would just be sort of like this. It would be backwards because it would be pointing from A to B. Because if you imagine A, oh, something like that. So let's say that we have alpha 0, which is a map from 0, 1 to t, and that is a parametrization of the line segment from A to B. So what would that look like? That's alpha 0. And then let alpha 1 from 0, 1 to t be a parametrization of the line segment from AA to AB to well, I guess that would be segments, but it seems that you would be able to sort of interpolate between alpha 0 and alpha 1. That's like these. That's pretty badly drawn, but that's sort of the idea. So, to continue, suppose that d of s is the degree of the composition of our function from before in alpha s, where s is between 0 and 1. And remember, since all of these are unit vectors, this function essentially maps these 2 points to a circle. So an alpha maps from an interval to those 2 points. So we're mapping from an interval to the circle, therefore. So then we have that the mapping from S to the degree of S is locally constant and therefore continuous on the interval. So it's integer valued and continuous, so you can imagine, because the degree has to be an integer, you can sort of imagine how, that it must be constant. So the degree of where s is 1 would be equal to the degree where s is 0. So I know it's kind of tricky to follow because there are like multiple layers of abstraction we're dealing with here, but just bear with me and we'll end up with something soon. So d0 is the degree of the unit tangent function of gamma, so it's basically just if you can imagine like tangent, 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 and so on. That's basically psi of alpha 0, or d0. Um, but let's talk about d1. And let's talk about why it's 1 or negative 1. So if we have, let's say, we have a curve, and this is our point with its tangent line, and let's say we have a circle, a very badly drawn circle, but a circle nonetheless. What are we doing with when s is equal to 1? Well, it's first we go from AA to AB. So the points, it starts off with both points at A, and then one point is kept at A while the other moves to B. So that's basically just one point is here, and the other point moves all the way here. And remember how we have the unit tangent vectors pointing in the direction from point 1 to point 2. So we're going all the way this way, this way, this way, this way, this way, and we've reached point B. So now we are halfway across the circle. So that's the first half. Then we go from AB to BB. So we are over here and we're moving there. And that basically means one point is fixed at B, and then the first point is moving from A to B. So I'm on green. That point is fixed at B, and then the other is moving to B. So what do the vectors look like at that point? They'll be in this direction. So we basically have sort of vectors going down. It's pointing down, and then it's going back to the side, and then it's doing some stuff, but it eventually ends up back here. So we go back a full rotation. So in that case, it's pretty clear that d of 1 must be equal to 1. However, if we go the other way around, you can see pretty clearly how d of 1 would be equal to negative 1. So we have proven with all this abstraction that the rotation index of a simple closed curve, plane curve, must be equal to positive or negative 1. So that's what we've done. So before we prove the second theorem, the Jordan curve theorem, we're going to look at something called a tubular neighborhood. And that is basically a mapping from phi, which is from the Cartesian product of negative epsilon epsilon and AB to R2 in this case. And the best way I can describe it is visually. So this is our epsilon, this is our negative epsilon, and this is our A, and this is our B. So it's mapping this rectangle looking thing to a curve. This is gamma A or gamma B, whichever you prefer. And oh, the top and bottom should be dotted, but just ignore that. And they should be of uniform length, but my drawing skills are not up to par, so this is a tubular neighborhood. We are mapping a rectangle on the Cartesian plane to a curve like so. So now let's look at the proof of the Jordan curve theorem. So I mean, you would think that I would have it easy because I have my book right here, but the book doesn't always show like all the explanations and all the steps, and I have to remember, to fill it all in and how things work. So, all right, let's start from the basics. We have a simple closed plane curve, gamma, and C is the trace of gamma. So, let's say we have a point in the plane that is not in the trace of the curve. So, let's think up of a function from an interval to the circle defined as basically, what we're doing here is we have a curve here, we have a point, and what f does, if you take a point here, it's just the unit vector pointing towards it. If you take a point here, it's the unit vector pointing towards it, and so on, and so on, and so on. And you can see it draws out sort of the arc of a circle. It might not be the full circle, mind you, so it might not be up here, but still part of a circle nonetheless. So now, what we want to show, we're going to say need to show, there are two path-connected components, NTS, one on which, oh, I forgot to define that. So we're going to introduce a function w, which is basically the degree of f of p. So that's basically the number of counterclockwise rotations that the arrows just undergo as you traverse the curve. So there's two path-connected components, one where w equals 0 and one where w equals positive or negative 1. So our proof relies on the idea of a tubular neighborhood. So let's zoom in on just a part of the curve, and we've got, you know what, let me use this. We've got a tubular neighborhood going on. And we have 2 points, P1 and P2, which are close to each other. They're very close, but they're on opposite sides of the curve, as you can see. Our claim is that we have this. So let's prove it. Okay, so first we want to figure out what the path denoted by this means. So what we're doing is, suppose that the P1 is in the interior, and suppose we start over here, and gamma of A, and this is gamma of C. So we begin traveling through the curve. The arrows are pointing in the direction of the point, and we end up here. So we did that. Um, But let's look at what happens when we do the negative FP2 part of that. So that would basically just be traveling in the opposite direction and looking at how the arrows turn with regard to P2. So they probably go up, and then they come back to here, and then they go back there to A. So we do that. And it should be, as we get closer, it becomes in such a way that these points are, that the arrows start pointing to the side like this and like this. That's how close they should be, that they approach that. But TAP formalizes all that, but I'm just trying to give you an overview. So this function is the combination of this and that. So let's see what happens when we combine them. So we start over here, we do that, we do a little bit of that, and then we go back. Now, I don't know about you, but to me, that looks like one full rotation. And that means the degree of fp1 minus fp2 equals 1. And therefore, it follows that the degree of fp1 minus the degree of fp2 equals 1. And there is no half of a degree, there is no quarter of a degree. So these two are in different path-connected components of R2 minus C. So now we have to claim something more. We have to claim that these are the only components. So how will we do that? Suppose we have a point P. It can be on the inside or the outside. And we have P1 and P2 here. Let's call this Q. And this is a badly drawn tubular neighborhood. What we do first is we construct a path, a shortest path from P to C, but we don't use part of it. Instead, since we are in the tubular neighborhood, we move parallel to the curve until we connect with P1 or P2. And therefore, any point in the real plane minus the curve is path connected. It can be connected via path to either P1 or P2. Now, suppose that we have a ball in R squared, which ends up being a circle with like everything filled in. It's pretty clear that one component must contain the complement of B, as you can see. And therefore, that component, which is the exterior, is unbounded. So the other component must be contained in B, and is therefore bounded. Before we close this proof, let me talk about boundedness. Boundedness is a concept that essentially you can basically get by knowing what it is, but to make it more vigorous, we say that boundedness is essentially a set is bounded if you can construct a ball, which in this case is a disk or a circle with the inside filled in, and it is contained in that ball, which we call an epsilon ball, since it will have radius epsilon, where we do not know what epsilon is. So after all this long proof, we have very much proven the very simple claim that, where is it? If you draw a curve, there's an inside and an outside. You split the plane into an inside and an outside, and that is what we have proven. There also exists something called a generalized Hopf's Umlaufsatz, and that basically says that for a plane curve, if we take for a simple closed plane curve that is piecewise regular, I'll define piecewise regular in a moment. If we take the integral from a to b of the sine curvature plus the sum of all the signed angles at its corners, we get 2 pi. So there are a couple questions here. What is a piecewise regular curve? And that is basically a curve that can be split up into partitions. T0, T1, dot, 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 Tn equals b, such that each subinterval from ti to ti plus 1 is regular. I'm just abusing notation like there's no tomorrow here, but you could think of a piecewise regular curve as something, it may have corners, but parts of it are regular. In fact, every part is regular except for the corners. And you're also probably wondering, we have these alpha I signed angles. So suppose that maybe we start here and we're traversing this way. Signed angles are essentially angles that have a sort of, I guess, sort of direction. So there's a proof idea, but I'm not going to go over it. I think we've had enough of proofs for now. I mean, we proved 2 pretty big theorems, so thank you for listening, and I'll see you guys next time.